Good morning, everybody. Welcome to the solution video to the 8th algorithms thread video. That one was on tree basics, so if you haven't seen it, you should definitely watch the video first and go try the problem set that I made corresponding to the video. These are the solutions to all of those problems. So if you got stuck and you want to know how to do one or more of those problems, the solutions will be in this video right here. A lot of people asked me to make the test cases public, and I would love to do that. I don't know how though. Like, there's not like a button on my end as an administrator, that I know of at least, where I can make those public. If any of you know where I can find that button to make it public, I would love to do that. I'm not trying to hide them. I just don't know how to release them publicly. So instead, what I'm going to do is I'm going to post the code that generates all of the cases. I'm going to post that code on GitHub, so you can download that code if you're interested. Some of the problems just have hard-coded test data. So for those problems, I guess maybe I'll just post the data. I'll also post the solutions on that GitHub, and I'll walk through the code in this video. So you should have pretty much everything you need if you aren't passing a problem to be able to figure out what you're doing wrong. Okay, so let's jump into the problem set. Here are the 6 problems. I'll open the problems. I won't talk about them too much because I think for the most part they're pretty straightforward. So problem A asks you to find the circumference of the tree. Now, in order to do that, what you have to do is say pi is equal to the ratio of the circumference divided by the radius. Now, in this case, we said pi equals 3, so 3 equals the circumference over the diameter. Sorry, I'm talking about tau. So in this case, pi equals 3, so 3 equals the circumference over the diameter, which means that the circumference is equal to 3 times the diameter. So we learned how to find the diameter of a tree in the tree basics video. We find this diameter, we multiply it by 3, which is an integer, so everything stays in integers, and that is our answer. What does the code look like for that? Well, you read in the nodes, and then you do 1BFS to find the farthest node from some arbitrary starting point. You know that's the endpoint of at least one diameter, so then you can find the farthest node from that node, and that will be the diameter of the tree, the distance between those two nodes. So basically, this is the entire solution to the problem once we have the find the farthest node and do a BFS. The BFS part is pretty easy. So this is just a regular normal BFS. You just use some sort of queue, whatever you'd like. In Java, those are called array-decs. C++ has a queue. Java also has a queue, but it's really slow for no good reason. So you have to just use array-decs instead if you want it to be fast. Farthest just looks at the distance from every node and finds the node with the farthest distance. So that's it. Okay, so that is the circumference of the tree problem. It's supposed to be pretty easy to kind of get your feet wet. The next problem also used the idea of diameter, and it used kind of sort of like a general approach to diameters that I think is interesting, which is looking at things as if you have some diameter of a tree. So there was this property that we noticed. So for dynamic diameter, basically what it asks you is if you have some tree, maybe this is your tree like this, and it's got other things coming out off of it, like this maybe. Maybe that's your tree. And you want to know, okay, you're going to add one node to a bunch of other nodes on this tree. So you might add this node to this edge here. You might also add it to here, and you want to know for every node that you might connect this last node to, what will the new diameter of the tree be? So in this case, the new diameter will be 5, right? So it'll be just these 5 edges, for instance. There are other ways of getting a diameter of 5, but this is one of them. You can't ever get a diameter of 6 if you add it like this. However, if you add it to this node here, now you have a diameter that's six nodes long. 5 edges, I guess. So the diameter would be 5 before it would be 4. So this is one way of doing it. Basically, all we need to know here is this node here part of any previous diameter? In this case, it was. Since it was, we had the previous diameter like this, and we just made it one longer. So we've increased the diameter by 1. In this original case, this node here, I guess it's part of a previous diameter, but it isn't an endpoint of a previous diameter. Which means this node here, if you add an extra edge to this node, you're not going to beat the previous diameter because currently the path to this node didn't tie it. which means adding one more edge from this node won't actually make the diameter any better. So that's all the problem has boiled down to now. So the question is, which nodes are part of some diameter? When I say part of, I mean like which nodes are an endpoint of some diameter. Now, how do we solve that? Well, we talked about earlier, there's this really nice property of trees, which is if you pick any node here and you find what's the farthest node from this node, it'll be the endpoint of one of the diameters. So if we look at this node here, we find the farthest node, maybe we get this node here. We know this will be the endpoint of some diameter. You can also kind of do that in reverse. So you know if you have some diameter, like this, if you apply the argument kind of backwards, if we have some other node here, we know since this is the diameter, the farthest node from this node here will be one of the two endpoints of this diameter. So if we want to find for each node in the tree, what's the farthest node from it, we can just say, what's the distance from this to every node in the tree, and the distance from this to every node in the tree. That's just two BFSs. So that's very easy to code. And now we know for every node in the tree, what's the farthest path that contains this node. We can do that just with two BFSs because we know the farthest path will either be to this node or to this node. Okay, very good. So now we can say what nodes are part of some diameter, and the answer is all of these nodes here. All of these are a distance of 4 to their farthest node. So now, anytime we add this fifth node to one of these nodes that I've circled in blue, that will increase the answer by 1. And every time we add it to a node that isn't circled in blue, it won't change the answer. That's the solution to the problem. So what does that look like in code? Let's open this up right here. Okay, that was unintended. There we go. So again, we do two BFSs to find what the original diameter is. And this is just like our solution to the previous problem. So we just get the original diameter. So now for each node in the entire graph, what we want to say is this part of some diameter? So if its distance from one side of the diameter is equal to the original diameter, then it's definitely part of the original diameter. But also, the farthest node from it might be the other node in the diameter. So we also do a BFS from this farthest node here. And then that will say, okay, is this the farthest node in the diameter? And yeah, by doing that, we have identified all nodes that are that have a maximum path that's equal to the diameter. So now any node where this node.diam value is true, that means it's an endpoint of some diameter. Now for each query, we, or I guess the queries are just the numbers 0 through n minus 1. So we just look at for each node, is it an endpoint of some diameter? If it is, we print one more than the original diameter, otherwise just the original diameter. All right, very good. So that's problem B. Let's look at problem C. So I hope you enjoyed the joke that I made for this. I thought it was pretty funny at least. But yeah, so I guess basically the problem is pretty simple, which is if you have some tree and you want to, like you start at some node A, so maybe this is node A, then you want to go to some node B, and then you get to take at most C steps. So maybe in this case, C equals 3. So here you take one step like this, one step like this, and one step like this. Now you want to say what node do you end up on if you start going from A to B. In this case, you end up at this node here. So this is the node that you print. Now if you can reach B, if you can get all the way there, then you just print node B. Okay, very cool. So that's the problem. How do we do it? Well, this uses kind of the next topic we talked about, which was binary lifting. So the idea behind this problem is if we use binary lifting, we can find what the LCA of these two nodes are. What the LCA is, I guess. In this case, the LCA is this root of the entire tree right here. So now we can very easily find the distance between these two nodes, which is just the depth of A, so that would be 2, plus the depth of B, which is 1, 2, 3, 4, minus 2 times the depth of the LCA, which is 0. So the distance between these is 6. Okay, very cool. So we know that since 6 is less than C, 6 is less than 3, then we can't reach B. So we don't print 6 immediately. Now the next step is, if we walk along this path, there are going to be 2 parts to it. The first is we'll walk up in this direction, and the second is we'll walk down in this direction. So as we walk up along this path, we just want to say, okay, which part of these 2 sections of this path will we be in if we take C steps? The first 2 steps are going up, and the next 6 minus 2 steps will be going down. Since this 3 is bigger than 2, we'll be on the second part of the path. If we were on the first part of the path, all we need to do is go up that many steps. We can do that very easily in log time using binary lifting. Now we're in the second part. Going down is very tricky. We don't really know how to go down, because when you go down, you have to make some decision. So we can't easily pre-compute what you would do going down that many steps. Instead, what we can do is, since we know how long this total path is, and we know how many steps we're going to take, we can go up from node 4. So we want to take 3 steps from A. The total distance is 6, which means we want to go up 3. If we do that in log time using binary lifting, then we can identify where we would end up on the path. That's the idea. What does the code look like? Well, we have all of our nodes and edges. First, we do this DFS in order to pre-compute the binary lifting table. So this is the same binary lifting code that I talked about in the tree basics video, and this is just one way of implementing it. You can also do it if you don't want to use node objects or node structs if you use C++. Then instead of doing it object-based like this, you could do it all in a table where you store the IDs of different nodes. That works as well. So let's just look at what this DFS does. Basically, in the DFS, we have each node has an array. And this is what node will you be at if you go up 2 to the I power edges. So 2 to the 0 will be just your parent. 2 to the 1 will be if you go up twice. 2 to the 2 will be if you go up 4 times, etc. From doing this DFS, we can just store what our parent is. That'll be if we go up exactly 1 edge. And then we can look through all of our kids and continue the DFS. So that's very easily. This is how to go up some number of steps. So basically, if we want to go up this number of steps in log time, then we can look at the lowest 1 bit in this number right here, and then we count the number of trailing zeros in it. So this is the number of zeros that some number ends in, this n steps. If we wanted, we could pre-compute this, and then we could just look this thing up in a lookup table. But this is just a very quick operation anyway, so I didn't worry about putting in a lookup table. So basically, this is take the next power of 2 that we need to in order to reach whatever this is. I do this recursively because I think it's easier to think about, but you could also do it iteratively if you wanted. And you go up this power of 2, basically, and you continue going up until the number of steps that you need to go up is 0. So this just takes care of 1 bit at a time recursively, and it keeps doing that, subtracts out the bit until all of the bits are equal to 0. So by doing this in log time, we can go up an arbitrary number of steps, and this is the code for it. LCA is very similar to what I talked about in the other video. Basically, if the depths aren't equal, whichever one is lower, we go up until the depths are the same. Now, if the 2 nodes are the same node after going up those amount, then the LCA is just whatever that node is. But if the nodes are different, then this num jumps is the biggest we could possibly go. So we notice every time we do this while loop, this number of jumps decreases by 1. This makes the final runtime order log n instead of log squared. So that's, I guess, an important thing to note. And this number only decreases. So every time we do a check, the number will decrease by 1. It can only decrease 20 times. Because it starts at 20, it's always 20 or smaller. And then at each step, we keep decreasing it as long as if we go up this number of steps, we're at the same thing. Eventually, we'll be at different things if you go up some number of steps. And we'll find the highest we can go where we reach 2 nodes that are different. That means their parent will be the same. That'll be the LCA. That'll happen in this if statement, and then we'll return. Otherwise, we find how far we can go so that it'll be different. And then we go up that number of nodes both for us and for this other node that we pass into this method. All right, so that's how we find the LCA. And once we have LCA and go up, the problem's pretty much solved. We get the LCA, we get the total distance between the two nodes, and then we just have these two cases. In one case, we go up from A, and in the other case, we go up from B. Okay, yeah, that's all. That's the Sloth problem. I guess one thing to keep in mind for both this and the dynamic diameter is that you want to use print writer or fast output if you're in C++. And that's because you print a lot of different numbers. So since you want your output to be fast, you have to make sure that you don't flush the output every time you print. So in C++, you don't use endl. In Java, if you use system.out.println, you should replace that with a print writer and then only close at the end. That way you just flush your output once and it's fast. Okay, the next problem is very similar to this. So if you're able to solve Sloth Naptime, you should definitely be able to solve this tree basics flow. So let's look at the problem statement real quick. But basically, what you'll notice here is there's this thing called max flow. It's a very interesting concept. It's more difficult. So I guess, yeah, it's quite a bit harder than just these tree operations. But the idea behind max flow is that if you only have a single path, if there's only one way of doing it, then max flow is very easy to compute. It's just the minimum along the path. So that's what this is asking. Basically, you can simplify the problem to just given a weighted tree. If you're given two nodes a bunch of times, you want to say what's the minimum along the path between those two nodes. And that'll be the edge that runs out first. So yeah, very cool. That's it. So how do we do that? Well, instead of just storing the LCA, we can also store, I've got some debug here because I was getting something wrong originally. But in addition to storing what node do we end up on if we go up 2 to this number, we can also store what's the minimum along the path if we go up 2 to this number of steps. So we store both of those, and now we can very easily, as we do this LCA, or as we have this ability to go up some number of steps, we can also say, if we go up that number of steps, what is the minimum along that path? So now once we have this LCA, we can just say, okay, what's the minimum if we go up to the LCA from both of these nodes? That'll give us the minimum along the path. So yeah, it's pretty much the same. I won't go through all of the details because it's basically just the same as the last problem. The only difference is, in addition to calculating what node we are on if we lift up this many, we also have to calculate what is the minimum edge if you go up this number of steps. And it's just the same thing, we just have to add an extra line or two to this for loop here. Then in addition to having this go up, we also have this min go up, which is pretty much the same thing, except it just keeps track of the minimum value. All right, very cool. That's the flow problem. Only 2 more problems left, and as you might imagine, these use the third idea that we talked about, which was the Euler tour idea. So the idea behind Euler tours I talked about in the algorithms thread video. So if you're new to that, you should definitely learn it. And this is the part that requires either segment trees or Fenwick trees. So whichever one of those you prefer is what you should be using here. Both of these, I made them pretty simple problems in the sense that all they required was either point update range sum or range update point sum. But those are equivalent when you're using a Fenwick tree. So if you want to use a Fenwick tree, this is a perfect way of doing it. Alternatively, if you want to use a segment tree, that works just as well. So if you're good with segment trees, you don't know Fenwick trees, that's perfectly fine. You can get a correct answer with those. Okay, so how do you do it? Well, let's talk about this first problem, problem E, and then we'll move on to problem F. Problem E, you have these 2 different operations that you can do. The first is you can change the value of some node. And the second is you want to say, if you look at the product of all of the nodes in some subtree, so maybe you have something that looks like this. We'll draw a fairly big tree so it's interesting. So maybe you have something like this. Maybe you say, what is the product of this subtree here divided by the product of this subtree? So if you take all of the things in this first subtree, multiply them together, then take all of the things in the other subtree, multiply those together, what is the value of the first thing divided by the second thing? Now, I guess there are some additional constraints, which is if the first thing is way, way bigger than the second thing, then just print 10 to the 9. So that way you don't need to print these just massive numbers, because otherwise it would get very difficult. Now, the first thing to notice here is that we can't actually store what these numbers are, because they might get really, really, really big. If we're at some node here, we might need to take the product of 10 to the 5th different numbers. Each one of those numbers might be up to 10 to the 9th big. So we're taking 10 to the 5th numbers, right? We're multiplying them 10 to the 9th times. So it's we're taking numbers that are 10 to the 9th. We take this number to the power of 10 to the 5th. This is a huge number. That number might have like 45 digits in it. Is that true? No. It might have 9 times 10 to the 5th digits. This many digits. So it's a very big number. So we can't actually store that number. If we tried to use big integers or something, we would TLE, because doing operations that big takes a long number of times, and we have to it takes a long time, and a big number of operations, and we have to do that huge operation a bunch of times. So it's very difficult. So instead, what we can do is use this trick, which is we only care about the relative value of two different subtrees. And all we're doing here is multiplying things together and dividing. We're not doing any addition or subtraction. So there's this really cool math trick you can do, which is if you know your logarithms, if you have log of A times log of B, that's not true. Let's look at this instead. So let's say you have the number A and the number B, right? If you have A times B, that's some number here. If instead we store the log of A and the log of B, what if we want to store the log of A times B? Well, all that is just like the log of A plus the log of B. The reason for that is if you have two numbers and you multiply them together, let's say we write A as like e to the x1 and we write B as e to the x2. Then the way exponents work, this thing right here is equal to e to the x1 times x2. E is just some number that someone figured out. Euler, actually, who I think is the same person that came up with the Euler tour, which makes it all full circle, right? Euler came up with this E, he also came up with the Euler. I just realized that right now as I was making the video. I might need to fact check myself on that later. It's possible, I guess, there are two people named Euler. Wow, that's impressive. This guy's all over the place. The whole problem is all about Euler. Cool. Anyway, back to the solution. Yeah. So if you have these two numbers like this and you multiply them, the answer. Sorry, this is not x1 times x2. It's x1 plus x2. The reason for that is pretty simple, right? This first number, like if you imagine e was 5, then this first number may be 5 times 5 times 5, right? That's 3 5s. So this would be 5 to the 3rd. If we multiply this by 5 to the 5th, then we have 5 times here, or 5 5s here that we're multiplying together. In total, this is equal to 5 to the 3 plus 5. So by doing this, what we've done is converted multiplication to addition when we've taken the log of all of the numbers. So now, instead of finding the product of a bunch of numbers, we can find the sum of a bunch of numbers where all of those numbers are pretty small. And if we want to find the sum of like 10 to the 5th different numbers, it's only going to be about 10 to the 5th big. It's going to be a pretty small number. Whereas if we find the product of 10 to the 5th numbers, that might be huge. So that's the idea. If we take the log of all of the numbers, then it stays small. If we want to find the inverse of the log, we can take e to that number, but we don't actually ever want to do that because that might be really, really big. Okay, so now if we need to do division too, right? So if we do division, a divided by b, This is equal to e to the log of a minus log of b. And you can do some more logarithm tricks to convince yourself of this. Basically, what this is saying is log of a divided by b is equal to log of a minus log of b. That's all this is saying. And of course, well, of course this is true because it's true with multiplication, and the opposite of multiplication is division. If it's true with multiplication to addition, then it's going to be true with division to the opposite of addition, which is subtraction, right? The opposite of multiplication is division. The opposite of addition is subtraction. So since it's true one way, it should be true going backwards. Of course it is. So yeah, that's the trick for this. Okay, so we've done all of this work. Now, hopefully I've convinced you that it's a good idea to think about these numbers, not as the numbers themselves, but as the numbers in log space, which is we want to store the log of each of these numbers. Very good, and that's basically the solution to the problem. So if we store the log of all the numbers, everything gets really easy to handle. And we can do the division at the end, and we just need to compare whatever this log is this log bigger or smaller than the log of 10 to the 9? What does the code look like for that? Well, we can use a bit, since all we're doing is adding a sum of double values, or of floating point values. So we can use a bit to store that. We want to do point update and range sum. I also store all of these as doubles, just for extra precision. And now if I have this type 1, type 1 means you set the new value to something. So in this case, what I do is I update some position by how much it would change by, and then I keep track of what this new value would be. So I make sure I take the log of all of the numbers that I input. That way everything stays in log space. So now, in this case, when I do a range sum, that's the same as a range product. So basically I'm taking the product of a bunch of numbers, except everything is still under log. All right, so once I do this, I can find this first number is x, the first node is x, and I go to the preorder of x to the postorder of x. The next node is y, I go from the preorder of y to the postorder of y. If you don't understand what that means, you should rewatch the Euler tour part of the algorithms thread video. And now we just need to print this difference. So the difference is either going to be the log of 10 to the 9th plus 7, or whatever the real difference is, whichever is smaller. So we find that difference, and then we print it. I print it to 10 decimal places. This is the judge solution, which is good enough. It's going to be close enough to the right answer. Yeah, so that's the idea. This is just how we get the preorder and postorder numbers in the node, and this is just a regular Fenwick tree, or binary index tree, whatever you want to call it. The only difference here is that this is using doubles instead of integers or longs like people usually do. Awesome. Okay, so that is problem 5. We now have one problem left, which is the Lorax. Hopefully you enjoyed the flavor text to this problem. Originally it was this other problem, which I guess works, but I think it was maybe slightly less interesting. It was just as interesting as of a problem, but less fun to read, I guess, right? It didn't rhyme. So I guess let's first talk about what the problem is, in case you didn't understand that part. If you're not a fan of poems, I can understand that this may have been a little bit annoying, because it's a little bit harder to extract the actual details. But at the same time, right, you gotta have fun sometimes, right? You have to enjoy a poem once. Stop and smell the roses, right? Stop and plant the trees. So you've got a tree, which is, I forgot the name of the place. Thneedville. You got a tree in Thneedville. Or in fact, Thneedville is a tree. It's a bunch of nodes and a bunch of edges. A bunch of places connected by roads. Bidirectional roads even. And you're going to have a bunch of things that happen. Each time you'll have either a seed. How do I draw a seed? I guess it'll be just like that. Sure, that's a seed. Maybe you have a seed here, and then you create a pot over here. It's kind of like a bucket, but I think that's an excusable enough drawing. So you'll have a bunch of queries. Each time you create a seed in one location and a pot in another location. In fact, you might create a bunch of seeds in the same number of pots at 2 different locations. So maybe we do that. Maybe on the next turn, we create a pot over here. and then we create a seed right here. So we do that a bunch of times. Now we have to answer the query. And the query is, if I give you some edge, maybe I give you this edge right here. I want to say if you match all of the seeds with a pot right now, don't actually match them, but pretend you match them. If you pretend that you matched everything right now, how many things would cross this edge? Now there are multiple ways of matching it. So here's one way. You can match this seed with this pot right here. And then I'll draw the other thing in white. You can match this pot with this seed here. Now that works, but a better way of doing it would be to match this group like this and match this group like this. Now you don't cover this edge twice. Like these two edges, now you don't cover them at all. Before you covered them twice. And you've saved your total distance by 2. You've decreased the total distance traveled by 2. So that's an improvement you can make. The question is, if you match in the best possible way, in this case it's just matching in this way, how many paths cross this edge here? So in this case the answer is 0, because nothing crosses this edge. Okay, so how do you go about solving this problem? Well, here's the observation we can make. If we look at just this edge, if we look at stuff in this subtree here, let's say the things in this subtree match up perfectly. There's no reason to have things cross this edge. If they match up perfectly, you would have to have 2 different things cross the edge. You'd have to have one seed cross the edge and also one pot cross the edge. That wouldn't be beneficial. We would just be incurring the cost of 2 that we don't need to be. So instead, if everything matches up perfectly, we'll just have all of those things match up. And then likewise, if we have too many pots, then every pot will have to cross this edge. And all of the pots that have a seed that stays in this subtree, well, we don't want any seeds crossing the edge if we don't need to. So we'll have all of the seeds match with pots that are in this subtree. So really what we can do is, if we treat every seed as a +1 and we treat every pot as a -1, we just want to say the sum of this subtree, if you take its sum, then take the absolute value of that number, what is that going to be equal to for one of these 2 nodes? Yeah, so I guess that's the solution. I always do it for the lower of the 2 nodes, I believe, but I think actually you could do it for either one of the 2 nodes and it would be fine. You just have to be careful not to, like if you do something like this, you don't want to count it like that, because then you've created an issue here. Or I guess rather the sum of this subtree would be this here, right? So you don't want to do that. So in this case, just find whichever of these 2 nodes is lower. Then for that node, find the sum of its subtree, take the absolute value. Okay, so what does that look like? Well, it's actually quite simple to code. We just find the lower of the 2 nodes every time we do a query. And then we do a query on this binary index tree, in this Fennec tree. And we take the absolute value of the answer and print that. Yeah, very good. So this DFS is pretty much the same as the last time. I wrote this quite a bit before, so it might be less clean, I don't know, whatever. But it works for sure. And you just store the pre-order and the post-order of each node. You increment when you go down. I increment right here. You don't increment when you come back up, because we're not doing stuff on paths. Even though it seems like we would be doing stuff on paths, we're not actually. We do stuff just with nodes. And yeah, that's it. So just build the tree, do a DFS, and then answer these queries pretty simply. So hopefully you enjoyed the contest. If any of these solutions didn't make sense, I guess let me know. It's probably best to post in the comment of the blog. That way, if there are other people that it makes sense to, they can answer. Yeah. So hopefully that works. If you send me a PM, that's fine. I'm happy to answer. But like, I get a lot of messages from people, and I don't want to say people below a certain rating can't message me. Like that's not, because there are people who are legitimately, still a pupil or still a gray or whatever. They just started. A lot of them have decent questions they want to ask, so that's fine. So I don't want to mute people. But like, if it's just a general question about this set, someone else might have the same question, so it's good for them to be able to see your question. So I'd post it in the blog if you can. But hopefully it made sense. I will upload all of the solutions and also the generators that I have to a GitHub account. And I'll post that in the description, probably also in the blog. All right, thank you for watching. Hopefully this was informative and helps you solve the problems. And have a great day. That's all. Goodbye.